Good morning. We'll start now. This is the last lecture on design of pipeline processor. We'll be looking deeply into how we handle hazards, particularly control hazards. So we had seen that there are various ways in which you can treat a branch instruction. It depends, the delay when you have a control hazard or branch hazard depends on in which cycle the instruction is found to be a branch instruction and how do we take subsequent decisions. So in which cycle we know that branch is to be done or not to be done, and in which cycle the target address is computed. So these are three things. One is to know that it's a branch instruction, then to know whether branch has to be done or not, and third is to which address you have to branch in case you need to branch. So depending upon the way you organize your microarchitecture, the way you divide instruction into cycles, these three may be done. These three actions may happen in different cycles, or some may happen in the same cycle. For example, decision about branch or target address calculation may happen in the same cycle, but typically after fetch, when you are decoding the instruction, then you know that it's a branch instruction. So, for example, in the design we are talking of, we we come to know in second cycle that yes, it's a branch instruction. That's when you're decoding. First cycle is gone for fetching, and once instruction is there in instruction register, then in the next cycle you know whether it's a branch instruction or DP or DT or whatever. The question of whether branch is to be done or not could be done in second cycle itself. It's a matter of evaluating the condition. All right. So evaluating the predicate depending upon what condition field specifies. So it could be done in second cycle or third cycle. In the processor where you're not looking at flag for branching, you are making a comparison in the instruction and then deciding. For example, some processors have instruction like BEQ R1, R2, and followed by a branch address. Okay, so that means the comparison is being done, and it might be done by ALU. So it would typically happen in the cycle where addition, subtraction, or all DP instructions happen. But if you're simply looking at flags, then flags have been set by previous instruction, and you could do this in second cycle. The target address computation would typically be done by ALU in the third cycle. Okay, but these are just example figures. These could vary depending upon how the instructions are organized at microarchitecture level. So now, how do you treat a branch instruction? So one simplest approach is that moment you see that the current instruction is the branch instruction, you flush out remaining instruction which may have come into the pipeline after this branch. Okay, because you will postpone the decision till you know whether you have to branch or not. Okay, till then you don't look at anything. Other is if inline instruction has come into pipeline. Inline instruction means the instruction which follow the branch instructions, and target instruction is where you are trying to branch. So you may freeze or stall the inline instruction. Okay, so you don't throw it away, but don't let it proceed further. Third is you let it go on. Okay, if you come to know later on that branch has to be taken, then you abandon this instruction. But till then, you let it go on and make some progress. So the idea is that if you don't have to branch, at least you have done some useful work. Uh, the next is delayed branch. That means uh, you assume that the branch will be delayed. I'll explain that in terms of timings. What it actually means is that uh, some instruction, one or typically one, but sometimes two instructions after the branch, that is in the inline stream, are always done irrespective of branch decision. Then the next is predicting what is the outcome of branch. Okay, so somehow we figure out if branch will be taken, will not be taken ahead of time, and then try to go along that line. So in case the decision turns out to be incorrect, in case the prediction turns out to be incorrect, you could retract what you have done. You could undo what you have done in anticipation. But if your prediction is good, then this undoing would be done much less often. Okay, so most often you will proceed without delay. But once in a while, if your prediction has gone wrong, then you incur some time penalty or delay for undoing these things and going via the correct path. So similar to predicting the branch decision, there is also a possibility of predicting the target address. Okay, because these are the two things branch instruction does. There is a decision making and there is a target address computation. So by predicting one or both of these things, you know ahead of time what is to be done and can proceed without delay. So let's try to see the timings of various possibilities in detail. Let us say ith instruction is a branch instruction, which is conditionally branching to instruction which we are calling as L. Okay, BEQL. How would you proceed? So instruction I, now this is a pipeline. Instruction I would be entering and going through these stages. may not do something useful in, let's say, last stages, but at least first three stages it will be doing something useful. Then in the next cycle, instruction I plus 1 is going to follow. Okay, so here this depiction we are making, a vertical axis indicates time. So this is one instant of time, that is the next cycle of time, next cycle of time, and so on. So when this branch instruction reaches RF stage, the next instruction I plus 1 is in instruction memory stage or fetch stage. Okay, and instruction I plus 2 will get fetched here, but by this time we know that it is a branch instruction. Okay, in this stage we will know that the instruction in decode stage is a branch instruction, and we would try to get rid of these. So you try to flush these two. And later on, let us say by the time you have reached this, so for the moment we'll assume that branch decision and address computation both are going to take place in third cycle. Okay, so in the third cycle, you know the address, you know the decision, so you can start fetching of the correct instruction. Okay, so it could be either I plus 1 or it could be L. So after this stage, you start fetching one of these, okay, and then continue. So you can see that we have lost 2 cycles in this process. So that's the penalty of this control hazard. Next possibility is that you freeze the inline instruction. That means when I plus 1 comes, okay, you let it be there, but you don't let I plus 2 come in. Okay, so we are not flushing this one, but we don't let it proceed further, and we don't get I plus 2 in. So,
Sir.
yeah.
So in the previous one, branch decision is taken care of in the RF stage, right? And the address computation in the ALU stage.
No, no. We instruction is decoded in RF stage, so we know that instruction is a branch instruction here. We are assuming that address computation and looking at the flags is happening in the third stage. Okay, so things could change a little bit if you move the decision point to second cycle. Okay, but just for this illustration, I'm assuming that decision whether you have to branch or not and address computation both are happening in the third stage. So that means further execution can start from this cycle onwards, where I'm showing fetching I plus 1 or L.
Yes, sir. So this branch decision will take place parallelly because ALU,
Yeah,
how can ALU do that?
right. So ALU is computing target address,
Hmm.
whereas another piece of logic which is looking
Yeah,
at the
obviously,
flags
yes.
and telling you whether to branch or not. Okay, so
Sir, over here, can you show the previous slide one?
yeah.
So in this, in the last case, where you have written I plus one or L, so at this stage, the DM contains the I minus one of instruction and RF contains I minus two of instruction, right?
So actually, ith instruction has nothing much to do after third stage. So it will just maybe go through the pipeline silently, doing nothing. Now, at this point of time, when this instruction is in instruction I is in DM stage, we are fetching the next instruction, okay, which could be I plus 1 or L. So is that okay or still doubt?
No, sir, I was asking about the previous instructions which would have come before the branch. So they would have been in DM and RF, right?
Okay, instruction I minus 1.
Yes, sir.
Uh, yeah. So we are not doing anything with those. The instruction which are before I, or you should say ahead of I in the pipeline, they are not disturbed. When we say flush inline instruction, which these are the instructions which are following I. Okay.
Yes, sir.
Okay. So in the next scenario, we leave instruction I plus 1 there. We didn't allow it to proceed further. So if a branch has to take place as usual after computing the address and knowing that branch has to take place, it will start here after 2 cycle delay. But in case we had to proceed with the inline instruction, that means branch decision was false, we will let instruction I plus 1 move forward. Okay, so it did nothing in this cycle, it remained frozen, but now it can move and continue. So if branch is taken, then we have 2 cycle delay, but if branch is not taken, we have only lost 1 cycle. Okay. In the third, okay, and then this inline series can proceed without any further delay. The third scenario is we let instruction which is inline go on as long as we are in doubt. Okay, so I plus 1 comes in, I plus 2 also tries to come in, they continue, but after this stage we know whether we have to branch or not. So in case we have to branch, we can abandon these and bring a fresh instruction at address L. But in case branch is not to be taken, we allow this chain to continue, and they can proceed without any delay. So here the delay is 2 cycles if branch is taken, and no delay if branch is not taken. Right?
Sir, what was the purpose of freezing for 1 cycle in previous slide?
I'm just showing various possibilities. So these may have different logic to do that. The purpose is that we you could argue what is the purpose of flushing. So we don't know what is to do. So therefore we are postponing the decision. Okay, so freeze is slightly better that we don't throw away, but we don't even proceed. So it is frozen wherever it is. All right. In case of inline, in case of this scenario, we are sort of anticipating that okay, if branch is not to be taken, we would have done some work. So it's like predicting. It's something like predicting that we are predicting that branch will not have to be taken, and we can continue with whatever we were doing. So that will bring us to proper prediction. That prediction could be that branch will be taken or branch will not be taken, but I'll come to that shortly.
Sir,
Let's look at, yeah.
sir, then isn't allowing inline instructions to continue better than
Yes,
freezing?
it is better.
Okay.
The only argument against this could be that uh, if you allow this to happen and then abandon, you would have consumed some energy, which gets wasted. Okay, in the flush approach, uh, you're not doing any unnecessary work. You are doing something only when you're sure of it. Okay, so from performance point of view, that is bad, but from energy point of view, it may be better. Let's look at uh, another possibility, which is called delayed branch. So in delayed branch, you are not making a choice between I plus 1 and L. Okay. Uh, so the branch decision, I'm rephrasing by saying that after instruction I, you either do I plus 1 or L. In delayed branch, we say that the decision or the choice is between I plus 2 and L. I plus 1 will be done in any case. Okay. So that means we are delaying. This is called delayed branch with one delay. There is a possibility of increasing this. For example, you may say, all right, I'll do two instructions unconditionally, I plus 1, I plus 2, and make a choice between I plus 3 and L. All right. So let us see effect of making a choice between I plus 2 and L. So instruction I plus 1 will proceed without any hindrance or without any question or doubt. But I plus 2 may be done only if branch is not to be taken. Okay. So the choice is between I plus 2 and L. Uh, I plus 2 could be fetched here immediately after I plus 1. But if L is to be done, then it can start only in this particular cycle after 2 cycle delay. If I plus 2 was to continue, we could continue in the manner, if we had allowed inline instructions to come in and continue.
Wouldn't this give wrong answer?
Pardon?
Wouldn't this give wrong answer?
No, so the instruction I plus 1 has to be an instruction which has to be done in both cases.
Oh, okay.
Yeah, so you have to order your instruction such that uh, I plus 1 is always done, something which is always to be done. So later on I have an illustration of how actually we arrange code for this to happen. Okay, now let's examine these scenarios from a different representation of the pipeline, the stage-wise view, and things will be, it will give you one more insight into how things are happening. So now the horizontal line, the time is proceeding from top to bottom. At t minus 1, different instructions are in different stages. Okay. The branch instruction has let's say branch instruction has reached this decode stage. I plus 1 is after it, I minus 1, I minus 2, they are before I instruction, and uh, they are in stages which are subsequent to RF. So in the next cycle, I has moved on to ALU stage, but these instructions which are following, we are saying that you flush them out. Okay, so they they are removed from the pipeline, and in the next cycle, so when you remove these from pipeline, you basically have no ops or bubbles which are introduced here. All right, instruction I has moved to DM stage. So it has gone through ALU stage. That means it has decided whether to branch or not to branch, and what is the target address. So in cycle T plus 1, we are bringing in the correct instruction. It could be I plus 1 or it could be L. So I'm showing it as I plus 1 oblique L. One of the two will be there, and things will keep moving uninterrupted from this point onwards. So there is a delay of 2 cycles in either case. Okay, so these two bubbles have been introduced in pipeline, and eventually they'll move out, but they have caused 2 cycles of delay. The freeze approach would mean that instruction I plus 1 has come in, and it will be left there, but we don't bring in I plus 2. So after this, once you have decided whether to branch or not to branch, and if the idea was to go inline, then I plus 1 is still there. But in case you have to branch, then uh, there is a bubble here, and there will be a bubble here also. Okay. I plus 2 would be fetched, which is following I plus 1, or L will be fetched here. Okay. So if you're going inline, there is 1 cycle delay. If you're branching, then there is a 2 cycle delay. Right. So after this pipeline continues. In this third scenario, we let I plus 1, I plus 2 continue. We are not throwing them away. But in case branch had to be taken, then these are abandoned. Then these are moved out. And you would start with L here. Okay. So in this cycle, in T plus 1 cycle, you will be either fetching L or I plus 3. I plus 1, I plus 2 would have moved forward and would continue normally. Right. So there is no delay if there is no branch, and 2 cycle delay if there is a branch. All right. Next, we look at delayed branch. So I plus 1 will not be abandoned at any stage. It will continue. But if branch has to be taken, then I plus 2 would be thrown away. Okay. If branch is not taken, we continue with I plus 2. But if branch is to be taken, then this is abandoned, and we have a no op here. And the next will be fetching L or I plus 3. So in this case, if branch is not taken, no delay. If branch is taken, then there is a 1 cycle delay. So you can see that you have cut down delay even further.
So delayed branch will require some reorganization of code, right?
Yes, it would require reorganization, and
Okay.
I'll give an illustration of that later.
Sir, so the prediction of branch decision, can you give an example? How can a code be intelligent and predict branch decision?
Yeah, we are coming to that. So,
Okay.
so next thing we look at is branch prediction. So what does prediction mean? We uh, we we predict that branch will be taken. That means it becomes, we look at a branch as unconditional branch, at least for the time being. Or if we predict that branch is not to be taken, then we treat this as no operation. Right? it does nothing. So there is prediction, and then branch, of course, will be doing whatever it is supposed to do, and eventually we will know whether branch is to be taken or not. So if our prediction was wrong, we need to undo. Okay, so these are two aspects of it. The strategies for prediction could be static prediction or dynamic prediction. Static prediction means that we before running the program, we know uh, we try to predict what the behavior would be and then go accordingly. Dynamic prediction means that as instructions are getting executed at runtime, we make a prediction. So static prediction is something which has to be encoded in the hardware. Right? Hardware would look at uh, what the branch is and make some prediction. So it will not go by the execution state of the machine. It will make a prediction based on some static information. So, for example, the prediction could be fixed. So when we said that we allow inline instructions to continue, we, in some sense, we made a fixed prediction. All right, but you could make a prediction which is based on some information. For example, instruction type. So you might say that let's say the testing for equality will all branch will take place, but testing for less than greater than branch will not take place. Something which could be, for example, based on uh, some statistical information. So if you have run lots of program and collected information, you could say that typically this instruction mostly results in branch being taken, and this instruction mostly results in branch not being taken. So you may have some information. Based on that, you may do that. Or you could say that if the target address, if you're branching forward, then branch is less likely to be taken. If you're branching backwards, which is the case of a loop, you might say that, okay, loop means it's going to iterate several times, so mostly branch will be taken. So in some simple manner, you may make a prediction. Uh, Dynamic prediction would be based on the recent history. Okay, what happened, for example, when this branch was encountered earlier. So imagine that branch is part of a loop. Okay. It may be loop termination testing condition, or it may be somewhere in between the loop, in the loop body. And you may have some history which you may have recorded. Okay, so you keep track of what is happening as the program is running, that a particular branch is being taken mostly or not being taken. And based on that actual history, you may make a prediction. So, for example, a simple idea could be that you predict based on the history of just one previous branch. You just look at last time what happened. It's simple to remember. If you have to remember longer history, then you need more hardware. Okay, so this is something which can be built easily in the hardware and branch processing logic, that you simply remember the previous history and keep on updating that. So if last time branch was taken, you say that, okay, this time also branch will be taken, and vice versa. So now imagine a loop like this, where at the end of the loop, you're testing some condition and going back if some condition holds. So now imagine that this loop is also part of some bigger code, and maybe there is a loop outside. So you do this loop several times. Okay, you come into the loop, have some iterations, go out, and sometime later again you will come to the loop, have some iterations, and go out. So every time when you enter the loop, uh, prior to that you would have exited the loop. This branch you would have encountered in the last occurrence of the loop, and you wouldn't have branched. Okay, so when you go through the first iteration, your prediction will be wrong because now you're going to, let's say loop is run 10 times always. Okay, it's a loop which is iterated 10 times. So first time you come here, you say that branch will not be taken, but branch gets taken, so you go wrong. Then next 8 iterations you will be correct. Okay, because branch was taken and it will be repeatedly taken. When you are exiting again, you will make a mistake. Okay, your prediction will go wrong. So out of 10, 2 times you have gone wrong, but 8 times you are correct. Or if loop was done 100 times, you are correct 98% of the time, 2% of the time you are wrong. So not bad. But here imagine that instead of this dynamic approach, you had a simple static branch prediction, which simply said that branch will be taken. Okay, then out of 10 times, you'll be correct 9 times and wrong only 1 time. So can we make the dynamic prediction at least as good as this simple static prediction? The answer is yes. If you look at last 2 branches, so we keep track of this using a small FSM, uh, which would have 4 states. So basically we need to remember now 2 bits of information. All right. Earlier in the previous approach, we just need to remember 1 or 0. Last time branch was taken or not taken. So we are remembering 1 bit. But this 2-bit approach can make things better. So let's understand this finite state machine. Uh, these are the states. 0 and 1 are the 2 states where we predict that branch will be taken, and these are the 2 states where we predict branch will not be taken. And we make state transition depending upon the actual branch outcome. So you make a prediction, but then see what actually happened, and based on that you update the state. Okay, so if you are predicting, suppose you are in state 0, you are predicting that branch is taken, branch is to be taken, and branch actually gets taken, so you happily remain in the same state. But if prediction has gone wrong, you make a note of that, but don't change your mind immediately. Okay, so if this if you have 2 wrong predictions, then you go to a different state. All right. So if after 1 misprediction you have a correct prediction, you come back to this. But if you have 2 misprediction in a row, then you come to this state and start predicting that branch will not be taken. So T represents branch taken, N represents branch not taken. So here now, if prediction is correct, you continue here. With 1 misprediction, you are on a watch, and if there are 2 mispredictions, you change your mind. Okay, but after 1 misprediction, if you have correct prediction, then you are back to this one. So now, if you have this kind of predictor and apply it to uh, this simple loop, then after going wrong once, you will not change your mind and you will keep predicting that branch will be taken. So next time when you come in the first iteration, you will be correct. All right, and you will continue in that state. So this can actually avoid uh, faltering on such a simple case where static prediction works. There is another variation of this approach where you explicitly uh, remember last 2 predictions. Okay, so again there are 4 states, but you would see that there are some differences in the state transition. These are the 2 states where you're predicting branch is taken. In these states, you're predicting branch is not taken. So as a misprediction occurs, you are in this state. One more misprediction, you come to this state. And then you can, if you continue with, then you continue in this region, and so on. So basically, what you're doing is you can think of this as a counter. You're counting up here. If you keep getting n's, you keep counting up, and once you reach 3, you are saturating. Okay, so it's a saturating counter. If you get t, you count down and saturate with 0. So in a way, this will tell you the difference between number of taken branches and not taken branches. Okay, if in the past you have taken branches more often, then you predict that branch will be taken. If in the past you have more often seen that branches are not taken, you will predict branch not to be taken. Okay, any question on this?
Sir, in the previous one, the FSM which you had shown.
This one? Yeah.
Yeah. So according and the loop you had shown. So in that I draw something.
Yeah. In this loop, yes.
Yeah. So in our initial idea was that we won't branch, right?
Okay. Now, initially, so I think you're bringing us to the question of where do you start? So actually, you might start anywhere. So initially, it might make a couple of misprediction more than expected, but then it'll latch onto its rhythm and start predicting much better. Okay. So for example, here, if you had started in state 0, let us say, you will encounter one misprediction, but that will not flip you on the other side, and you'll continue to remain in state 0 or 1. Okay. But suppose you start with state 2 or 3. So initially you will go wrong. You'll see more misprediction. But if there are lots of branches taken, then you will come into state 0 and 1 and then remain there. So you don't have to so much worry about initializing it correctly. All right. So there may be in a long run, those initial transients will become negligible.
So like
Sir,
the 0 or 1 state, they tell us to take a branch, right?
Yeah,
So
yeah,
then initially they would predict correct for the loop condition because for the first 10 times you are looping.
yeah.
You said I think the other way around that if you are in 0 or 1, we would predict wrong for starting.
No. What I'm saying is, if you start with state 2 or 3,
Okay.
if this FSM or this automata starts in state 2 or 3 initially, it and you have lot of you are getting branches very often, it may be mispredicting initially, but then it'll correct itself.
Okay, sir.
Yeah.
mm, sir, in like this example, you gave a loop, and the loop has something like if there's a branch, then it's more likely that the next thing
Yeah.
will also be a branch.
Yeah.
So, what is an example of something that, repeatedly has no branches? So, I think something like recursion, maybe. Can you give an example of that?
Well, example could be that there is let's say in the loop body you are testing a condition which is occasionally true. Mostly it is false. So it depends upon the program logic. There could be uh, many if statements which are the statistics could be anywhere from the condition being mostly false or condition being mostly true or being equally either way and so on. So there could be different
Sir,
conditions, condition testing which are having different behavior. Yeah.
Sir, if it's in a loop body, you are testing a condition and say if that condition is true, then you break out of the loop. then isn't that kind of like, because the loop will always iterate, so it's alternating between branch and no branch, and then this will kind of fail.
Well, for each branch we have, imagine that for each branch we have an FSM like this. Okay, so each treated differently.
For each instruction
for each instruction,
yeah,
we
okay.
are remembering this kind of history. So actually brings us to the question of where are we keeping this information? So we have to remember previous branch decisions. We can also try remembering previous target address which is computed. Okay, because to process branch quickly, we need to know the decision. We also need the address. So from previous occurrence of that branch, we can also compute target address. All right. So in branches like what we have considered in uh, ARM instructions, you have a constant offset which gets added to PC. Okay, so every time you encounter that branch, the target address is same. So if you have calculated it in earlier occurrence of the instruction and you remember it, you don't need to calculate again. Okay, same thing will hold. But there are instructions like when you are exiting from a function, you may say move PC comma LR. Okay, or you may pop PC from the stack. Okay, you may pop out LR from the stack and put in PC. So in that case, last time you encountered this instruction, the address may be different, and this time it may be different. So there are both kinds of scenarios, and in those scenarios where you have target address not changing, remembering it could help. You could go a step further and say that okay, if previous target address holds, then we also know which instruction was fetched from that address, and we could even remember that instruction. So you could go on like that. The idea is that these things have to be stored somewhere. They could be stored in cache. Well, cache we haven't discussed it. We are going to discuss it subsequently in the course. But cache is a fast memory which is between processor and main memory. Main memory typically what we have been calling as program memory or data memory. These technologically these are slower, much slower as compared to the CPU or the processor. So you put a fast memory called cache, which will hold the information of current interest. Some data and some instruction will be there. So you could store this information along with the instruction in the memory, in the cache memory, or you could create specialized memory modules in the design, which are called, for example, branch history table. So this is like a table. It's a piece of memory which is remembering those previous branch decisions. Or if you are remembering target addresses, so you call it branch target buffer. So these are typically the names assigned with these buffers. Or if you are remembering the instructions, you would call it target instruction buffer. So these are additional pieces of hardware which are there. So there is a cost to implement dynamic branch in terms of these things and associated logic. If you're keeping that information in cache itself, then of course, apart from 32-bit instruction, you will have to have a few more bits to remember whatever you want to remember. So here is a picture of, let's say, branch target buffer. So it's like think of this as a lookup table. The first field in each entry is the instruction address. Next thing is the target address. and then there are prediction bits. So if you have that 4-state FSM, then you need to remember 2-bit. Its state is remembered in the form of 2 bits. So you look up these 2 bits, you will decide the next state and replace those 2 bits with those with the next state, and so on. So firstly, you look up in this table by the address of the branch instruction. So as you fetch branch instruction, that instruction address would be used to look up through this. Now I don't mean that you do sequential search through this. So this is a special memory, kind of associative memory, where it can simply locate if this there is an entry for this address or not. So it will directly get to that point, and there'll be either a hit, that means that entry exists, or it may not be there. That means for this branch you may not have remembered the history. What will happen is that because this would be of a finite size, let us say you don't want to spend too much hardware cost, you have a 100 entry branch target buffer. Okay, so that means your program may have some 500,000 many branch instruction, but at any time you can remember information about 100 of those which are of more current interest. All right, if you want to add a new entry, you have to throw away some entry. So therefore the branch which you are looking at currently, it may have an entry, it may not have an entry. So hit means that in the lookup table you find that there is some information about this branch, and you look up these bits. Based on this, you predict branch will be taken or not. If branch is to be taken, then you use this address. Okay. Otherwise, you ignore this address, and in any case, when the actual information is known, you update the prediction bits. So update the states. Okay. If there is a miss in this, that means for this branch you don't have an entry, then you forget about prediction. You simply go in line. Okay, or maybe that is, you consider that as a prediction. Okay, that's the default. And after that, you may like to make an entry into this table, new entry for this branch for which you found the information missing, but that is at the cost of some branch which has to be thrown out of this. Okay, so you bring in a new entry, some old entry has to be thrown.
Sir,
Yeah.
sir, but if we are searching in this buffer table every time there is a branch instruction, won't that make it slow
Yeah,
actually?
I specifically mentioned that we don't search. We don't search sequentially. Assume that there is, let us say, comparison logic with uh, each of this for each location. That's why we can't have it too big. So we have 100 comparators which will compare the given address with the addresses stored here. Okay, so it's an expensive thing, but it will let you make a check into this buffer in one cycle. Okay, so
Sir,
as
it is like a lookup table.
it is a lookup table, uh, but its hardware implementation would mean that the given address has to be compared with all the addresses which are stored there. Okay,
Sir, all the addresses are compared simultaneously.
simultaneously, yes. So I'm sure you'll get feel of this being an expensive piece of hardware.
Yes, sir.
Okay. So question is, when do you access this? In which cycle do you access BTB? You could, before checking the condition, okay, before deciding whether branch is to be taken or not, before address computation, or just after decoding. So there are various ways. Or the fastest is that as you are fetching the instruction, you're fetching the instruction because you know the instruction address, and with that address you can do the lookup. So that's what is most commonly done. All right, now we talked about handling each branch separately. So each branch has some behavior, and we try to capture that behavior through this information we are keeping. But there is often a correlation between branches. For example, consider this fragment of code. So you are checking for some condition X. Here you are checking for condition Y. Then you have Z, which is AND of these two, and then you are checking for Z. So imagine that you have come to this point via some path. You know, these branches may have taken, may not have taken, but you have you know what was, depending upon whether branch was taken or not, you know whether X was true or false, whether Y was true or false. If that is known, Z would be dependent upon that. Okay. So when you are evaluating Z, you know something about it. You have gone through these branches before reaching here. So you can make a better prediction here if you remembered what this fellow did and what this fellow did. Okay. So idea is that there is some correlation between the branches, and therefore it's also useful to look at various branches collectively. Okay, when you're considering a branch, you need to see what is the history of other branches before you reach this point. So that's uh, we have what is called two-level branch predictors, which look at branch history um, in some global sense. Okay, what you try to see is that before you encounter a particular branch, what was the behavior of branches which you encountered before? Not same instruction, maybe any different instruction. So you maintain that kind of history in a shift register where you have let's say you have n-bit shift register. You can track what happened to last n branches in time. Okay, as you encounter one more branch, you push in one bit more and last bit goes out. So this tells you about last n branches. Okay, collectively it captures pattern behavior of groups of branches. And the second thing we try to do is that we look at the behavior of this a particular branch individually. So that is through a table which we call pattern history table, which will contain states of predictor efficiency. So this captures behavior of individual branches. So we are doing two things. One is that we are looking at last n occurrences of some branches, whatever have occurred before this. And then we also have focused information about uh, this particular branch, what happened to its last few occurrences. So, yeah.
So could you explain the difference once again between the two?
So I think this diagram will explain it
Yes.
first. So first we are looking at this shift register. It has bits 1 and 0, which means that okay, depending upon in which direction you look at. So this 0 means that the branch which occurred before this was not taken. The one before that was taken. One before that was taken, not taken, and taken. Okay, so this is the behavior of, this is a global information about other branches which have encountered. So when I say other, actually it could also include the same branch, depending upon what path has been followed. Maybe suppose we have, let's say, 10 bit here. So out of those 10 bits, 1 or 2 bits might be corresponding to the same branch, but that doesn't matter. It is that the last branches which occurred before this, what was their state. Okay. So now, given this pattern, we index into this, we look into this, and this tells us a state of a 2-bit FSM or a 4-state FSM. We use that to make a prediction that branch will be taken or not taken, and then eventually when that branch gets taken or not taken, when we know the actual result, we'll update that machine and also update this. Okay, so the indexing into this actually is done by a combination of what the current program counter value is and what this register is telling you. Okay, but the two put together may be a lot of bits. Okay, so you have 32 bits here, maybe you have 10 bits there, so this could be a huge table. So what is done is that you actually take a few bits from here and some bits here, maybe all bits from here and some bits from there, and use that to index, okay, into this table, because you don't want this table also to be very large. Although this is indexed, there is no lookup being done here, right? This is getting indexed, so that comparison logic is not there. So this is a way of combining global information and local information about global behavior and local behavior of the branch and the whole program. Okay.
Sir,
Yeah.
for the previous thing, like for it to be like effective, you would need to do all of this in one cycle, but like otherwise it
Yeah.
wouldn't be of any use, and you
Yeah.
can just do it.
Yeah.
Also, sir, um, is branch prediction really worth it? Because this looks like so much circuitry more than just the normal CPU, and it's like I think it's more than just a normal CPU itself. So branch prediction has most of the circuitry, and you're getting an advantage of maybe 10%. Like it depends on how many branches there are, and if there aren't
Yeah,
many branches.
so actually, yeah, what you were sort of discarding as 10% actually is quite valuable. So people would go for that 10% improvement, by putting all this hardware. Yeah, so it might look too much of hardware for too little improvement, but the systems, real machines have this.
Sir, in this, the previous history comes from PC, right? Like, sorry, of the same branch, the history of the same branch comes from PC, right?
Yeah.
So, if we don't use complete PC, then wouldn't that be wrong?
Yeah, then you are aliasing. Let us say you are looking at last 8 bits of PC, lower 8 bits of PC. So that means all those branches which have same last 8 bits, you have sort of grouped all those together, and you are looking at collective behavior. So that you are making a compromise there, but that's in interest of keeping the hardware cost reasonable.
But then what exactly does that represent? Like all branch instructions having last 8 bits same.
So you are in some sense kind of averaging the behavior. Okay. If they had all very diverse behavior, then probably the average may not be of much value. Okay, but if the behaviors were similar, then you have a good representation of that average.
So usually you would expect like only one branch instruction to be there for the last 8 bits, one or two maybe, right? So because like I guess in a larger program, no, but otherwise I don't think there is a correlation between branches that occur every 8 bits, same as something like that.
Yeah. So number of branches which may alias to the same bits of PC may be less, or one could say that Um, so in some sense, you're also looking at branches which are in sort of current window. So a program always has some kind of locality. You're always iterating in uh, some part of the code. Your whole code may be some millions of bytes, but at a given time, in certain interval, you are mostly localized into some area. All right. So therefore, the aliasing may not be too much. You may uh, you're not dealing with too many branches at the same time. You're focusing on some part of the code at any given time. Okay, now let me move to an
Sir,
illustration of how we organize instructions to make things better. Yeah, you have
one
more
thing,
questions?
this is a level one. Can you say like how is what does level one do here?
Yeah, level one was trying to take advantage of this kind of scenario, that you're not only looking at what this branch did last time, you're only looking at what uh, recent occurrence of this branch and this branch did. Okay, assuming that you have reached this point after having gone through this and this. Okay,
Yes,
so
sir.
like if x was 0, y was 1, then this will go one way. If both were 1, then it will go another way, and so on.
Yes, sir. So how is it different from level two? Like here, there also we are maintaining. We need PC to look at the history, and also we need the global register to
Yeah.
know the
So
branch.
firstly, to let's say to understand this for a moment, assume that there were not too many bits in PC, or we were willing to have large enough PHT. Okay. For a moment, let's say we are looking at all the bits of PC and this register, all the bits of this register. Okay. What it means is that for every branch and every pattern here, we have an entry here. Okay. So what this means is that when we have reached this point, then given recent history of these two branches, we will look at one FSM. Okay, if x was 0, y was 0, then there is one FSM for z for this branch. If this was 0, 1, there is another FSM. If it is 1, 0, another one. So we have four different FSMs which will help us in predicting. That means depending upon which route we came to this point, we look at a different FSM which corresponds to previous occurrences of the same route reaching B3. All right, so based on different global history, we have a separate entry for each branch instruction.
Yes, sir. Got it.
But that's a bit of exaggeration because we are not looking at all bits of this. Therefore, some branches are aliased. Okay, uh, now how do we reorder instructions or play around with the instruction to cut down some delay? So this is a job which, if you're doing programming at assembly level, you would do this manually, but typically it's job of the compiler when generates code. So we look at a simple example, and you can quickly see what this is doing. So there is one loop here. Okay, what we are doing in this loop is that we are storing R1 in address which is given by R2. So you're storing 1, 2, 3, 4, etc. These numbers are stored there, and we are going up to 10. So 1 to 10 are stored in location 100 onwards. Then the next part of the loop is actually counting down. R1 you could see is decrementing and you're checking for 0. So in the second loop, we are reading those values back from memory and accumulating them in R3. So anyway, the meaning of this program is not so crucial for this analysis. we need to look at the timings. So suppose we want to check how many cycles this program is going to take. Okay, let's ignore the stall which will occur due to pipelining hazard. So we start this instruction in cycle 1, start this in cycle 2. So I'm looking at the starting cycle of each instruction. And since there are no stalls, everything is happening fine. After this, I'll go back to L1. So in cycle 8, I'm here again, right? And then I'll continue second iteration. So I can straight away say that, okay, I'll reach here after 4 cycles, because from 3 I went to 7. So from 8 I'll go to 12. In the next iteration, just a minute. Oops. Yeah, in the next iteration, so I'll be there in cycle 13 and so on. So with a gap of 5, okay, 3, 8, 13, 18, and so on. And lastly, 48, and I'll be here in cycle 52. And in cycle 53, I come out of this loop and continue. Okay, 54, 55, 56. And then initially I'm not jumping out, so I'll continue. Here there is an unconditional branch, and I go back to L2 in cycle 62. So you can see the gap. Let me get the laser pointer. So first iteration started in 55, next started in 62. So there is a gap of 7 cycles. Therefore, I come here in cycle 68, and same thing could continue. The last iteration will end in cycle 124. Okay, I'll go back here 125, 126, 127, and in 128 I'll be out. Okay, so is this cycle counting clear?
Yes, sir.
So I've done that because I knew that each iteration is done 10 times. Okay, so you could see how long each iteration is taking, multiply by that, and then you can count the total number of cycles. So if there were no pipelining hazards, in 128 we reach this point. But now let's be realistic and assume that there is a 2 cycle delay when there is a data dependence, 2 cycle delay when there is a branch, and we recalculate now. So third instruction, there is a dependence. Okay, your computing address, you're getting address in R2 which is being used in next instruction. So I've added 2 cycle delay. So instead of 3, I'm putting 5. Right, and continue. Again, there is a dependence. You are updating R1 and then you're comparing R1 with some value. So there is a 2 cycle delay here. And then you are branching. So assume 2 cycle delay will be there. So instead of cycle 12, we'll start next iteration at 14. Okay, and go through same thing. 5 and 9 is 14, so 11 and 9 is 20. And then the last iteration, after that we come out of this loop. So from 92 to 95, I have again accounted for a delay of 2 cycles. Then continue here. Now after subtraction, you're making a comparison. So again there'll be delay. So I've added 2 cycle delay here. Then there's a branch, but I'm assuming there'll be delay of 2 cycles whether you are branching or not branching. So let us say we were following the flush approach. There is a dependence between this LDR and add. So again 2 cycles. Then there is an unconditional branch, but even unconditional branch will account for some delay. So added 2 cycle. Next iteration starts in 112. Ends in 124. This is the last iteration. Ends in 244. So after 244, I'm going back to L2, then comparison, then branch, and then I come over here. So I'll be here in cycle 254. So you could see that a lot of delay have been added, and the program is taking many more cycles. Now let's try to cut down these delays by some of the techniques we have used. So you can see the dependence there. Okay, there is a delay due to data dependence at these points. Okay. So now first thing I'm doing is that if I execute inline instructions after the branch, then some improvement would happen. So for example, look at this branch BEQ over, and I was mostly not branching. Okay, so if I had continued with these instructions, it would have been fine and I would have saved some time. So that delay is removed from here, and that delay gets removed from every iteration. So the total time is reduced to 234. We could have done same thing here. If, for example, we had predicted that branch will be taken and we could have continued with that. So some delay would be cut down here, but that's not shown here. Now we do some reordering of instruction. So look at these two instructions, for example. So we had this instruction and this instruction. They can be done in any order. But why would we reorder that? Because we want to move apart these instructions which are dependent. Okay, add R1, R11 and compare R1, 11. There is a data dependence between these. So if you interchange these two, then in the delay between dependent instructions, we would have done something useful. So same thing is possible here also, because this instruction LDR and add, they are dependent. So by interchanging these, we will move dependent instruction away. That will cut down the delay. So here the delay is reduced to 1 cycle because we have moved this instruction 1 cycle away. Similarly, the delay has been reduced by 1 cycle here. So essentially 10 cycles we gained here, 10 cycles we gained here. 234 has reduced to 214 now. We can do further reordering. We can move this subtract instruction. For example, let's say let's look at this first. This subtraction can be done before coming back to the starting point of the iteration. Okay. So what is happening now is that you're going till the end of the loop and then subtracting for the purpose of this testing here. So instead of that, suppose before you go back somewhere here, you do this subtraction. So you have already done the subtraction, and then you only need to compare that with 0. So what will happen for the first time? For first time, we will do subtraction before entering the loop. Okay. So with this, we have moved a copy of subtraction here and a copy of subtraction there. So this comparison and this subtraction, there is a dependence between these that is taken care of, and between this subtraction and following this comparison. So those delays are cut down. Okay, the delays which were there because of data dependence, and the code is become faster further.
Sir?
Yeah.
Sir, how does the compiler know that there is no that the code would not be affected, the answer would not be changed if we are reordering?
Yeah, your compiler has to okay, let us see. So compiler has to check that if you are moving an instruction from one point to other point, it has to make a lot of checks whether any other assignment to that destination is happening, or is there a use of that variable in that period. So for example, you think of this sequence that you have add, b, subtract and compare. Okay, so think in a sort of roundabout fashion. So essentially, subtraction was after b, after branch, and we are moving it 2 steps earlier. Okay, so now this subtraction is adding, subtraction is subtracting something from R1, and R1 is not either being read or written here. So therefore this change is harmless. It's not affecting the end result. So compiler will not go into how actually it does. It may be, so if you're moving from point A to point B, there may be multiple branches in between, and you have to study the effect of all those. So it's a sophisticated piece of optimization which compiler would do, but these are now fairly well understood. So these reordering will cut down delay further, and now I'm also showing the delayed branch. So delayed branch means that after branch you should have an instruction which has to be done under all circumstances. So after now in the first loop, after this branch, if I was continuing with the loop, I would go to L1 where I'll do a store. So why not bring that store instruction right here after the branch? Okay. Now, if I were to go back, I would have done store, so it is fine. But if I'm not branching, if I was to exit the loop, then I'm doing an extra store. Okay. So one could figure out if that extra store is harmless, then moving this instruction is fine here. Okay. And similarly, moving this compare after this branch. So doing an extra compare is of course harmless if you were not doing anything else with the flags. So compare will be done here, uh, whether you're branching or not branching, and then you branch to this point which will have BEQ as the first instruction. So these delayed branches will reduce further, And the instructions which we put after branch, these are called instruction in the delay slot of the branch. So a branch may have one delay slot or two delay slots. And if a compiler can find a harmless instruction to put there, it will put. Otherwise, it will put a no op.
So
So
in this case, is
yeah,
this goes logic? Is this like code logically correct? Is
yeah.
this, if I put this in ARM, will it read that?
If you put this
Store
in,
and compare. Like if I run it in ARM simulator, let's say for example,
well,
so will this compare and store be interpreted as the
so this
instructions in delay slots?
delay branch is a hardware feature which has to be exploited with the help of software. Okay,
Okay.
so the fact that branch is a delayed branch is a hardware feature, in the sense that the hardware chooses between instruction L and I plus 2 rather than L and I plus 1. So that's a hardware logic. But what you put in the delay slot is compiler's choice. If compiler can do analysis, find a harmless instruction, it will find, it will put there, otherwise it will put a no. Now your question is whether if you run this code on ARM, will it run correctly or not? Depends. The implementation you are using has delayed branch or not.
So how do I indicate that like semi implementation has delayed branch?
Okay, a, a compiler is generating code for certain version of a processor, and it has to know that. You are running on a simulator which is not implementing delayed branches. Okay, so if you
Okay.
run over ARM sim, uh, ARM sim is not simulating delayed branches.
Okay,
Okay.
sir.
Yeah.
Also, sir, one more question.
Yeah.
Here, when we have delayed branches, can we also have non-delayed branches, right? Like, is it
Okay.
possible?
Yeah,
Or
yes.
only delayed branches?
Processors uh, give a control to the user, or I should say to the programmer, to skip the delayed branch uh, if it is required. Okay.
Okay.
Sir,
Thank you.
With
uh,
the branch instruction, there would be a field which would determine whether delay slot is to be used or not to be used.
sir, uh, to data forwarding, which is, I guess, it would be implemented in most processors. Doesn't that cut down the dependency between two instructions? Like, does it? I don't remember it
Yeah.
well, I think, but
So
doesn't it make it one cycle?
yes, yes. So data forwarding is a hardware solution for handling data dependencies. Reordering, as we did here, I'm talking of this reordering, which we did to take care of data dependencies. So this is a software solution for the same thing. Now, even after data forwarding, uh, all the data dependencies stalls may not go away. So in fact, one could even work with a combination of the two.
Okay, sir, but sir, will the compilers be aware that which swap maybe doesn't matter because it will already be fixed
Yes,
because of data
compiler,
forwarding?
compiler must be aware of the microarchitecture. Compiler must know whether there is data forwarding or not. Compiler must know whether there is delayed branching or not, whether delayed branching can be bypassed or not. So all these things must be known to the compiler before it can generate a proper code.
Also, sir, regarding the ARM architecture that we were implementing, so in the instruction set manual, each instruction had specifically written that this will take this many cycles and this will take this many cycles.
Yeah.
So
So
does a
that
processor need to be made exactly like that?
yeah. No. As far as our lab exercise is concerned, let's not get constrained by that. Okay. We don't this exercise to be more complicated than it is feasible within the given time frame. So yes, there are timing. If you wish, you could study those, but don't have to stick to those as far as implementation is concerned.
Sir.
Yeah.
Regarding the assignment, I had a doubt. So, like, we in the main
Okay.
processor.
Can you hold on to this question?
Yeah, yeah.
I'm about to finish. So
Mhm.
in case some students have to leave, they could leave. Let me just finish this. The last bit was left. Um, okay. So in summary, this is what we have gone through. Original code without stalls, so many cycles. Original code with stalls, so many cycles. Uh, when we execute inline instruction after branch, that means we didn't flush it. We have some reduction cycle. After first reordering, 214. After second reordering, 182. Using delayed branch, 162. So you see that the attempt is to get to this point, 128. So let me stop here. I'll take some questions. So there were one or two examples of branch elimination using predication, but maybe I'll look at that next time. Yeah, so there was a question about assignment.
Yes, sir. Sir, I was asking that, sir, in the main processor, we'll have a control FSM, which will basically assign the control signals like write enable and register read write and those, depending on which state it is, right, inside the process, which depends upon the rising edge of the clock. And then, sir, the thing is that I saw when I am assigning some, suppose in the ALU stage, I am assigning the operand 1, operand 2 of the ALU in the third stage. Then I see that these operands they get assigned in the next cycle.
Oh,
Then
yeah, I get what your question is. So if you look at my instruction very carefully, what I have said is that in the clock process, which is implementing FSM, you make assignment only to the control state and to signals A, B, IR, DR, and RES. That's all you do in that clock process. All assignments you want to make to the inputs which are going to uh, other components, you do this outside this clock process. You can either do that using concurrent assignments, or you may create a process which represents a combinational circuit. That means this is not a clock driven process. This would be sensitive to uh, all the signal which you consider inside this process. But again, inside this you could have a big case statement which make assignment to different signals uh, in different control states. Okay.
yes, sir.
What you need to do is make sure that whatever is appearing on the right hand side of some assignment, all those signals appear in the sensitivity list. And also to each outgoing signal, you make a default assignment. So that it is ensured that each signal is driven in all possible conditions. Otherwise, it will not be a combinational circuit. It will become a sequential circuit.
Yes, sir. So
Sir, could
also
you
one more thing, like I tried this approach, what you said, like I did the concurrent assignment outside, but then I saw that yeah, it is getting updated in the next cycle. Like suppose I am doing RW equal to 1, and then in the next cycle, the rising edge of the next cycle, my register is getting written.
No. So where are you assigning RW equal to 1? If you are assigning in the clock
Process.
process,
Yeah, clock process.
no, this is what I'm saying. Don't do that.
Oh, acha, acha, okay.
All
Then
these,
we'll have only the next state in the clock process.
yeah,
It'll
yeah. So apart from these registers, A, B, I, R, D, R, RES, all assignments you do outside.
okay, okay, sir.
Sir, could you explain what are these A, B, like, what is the function of the registers A, B, RES, DRIR? Because
Yeah,
since A
so,
won't be used in ALU, the ALU input comes from the control part. So what does this A
uh,
do, A or B registers?
well, the input which goes to ALU could come from register A, it could come from PC. Okay, input which goes to second point of ALU could come from B, it could come from the instruction with the various sign extension and zero extension and those things. Okay,
Fine, fine,
so
fine. Thank
AB
you.
will be used to define what goes into ALU. So essentially, the concurrent assignments or the combinational process would be modeling the multiplexers which are feeding these inputs.
So the AWBW that you were saying,
Yeah.
we can keep them in a process as well. Like if we just ensure that before the rising edge of the clock, we
No, no.
assign them to absolute values.
In the diagram, I have shown AWBW. That is imagining if A and B were also components outside. They were also separate components which were individually clocked. Okay. Then the controller has to generate their right signals.
Oh,
But
okay, so but that can be done in a process, right?
I'm simplifying it, saying that A and B can directly be assigned in the clock process of the controller.
Oh, okay, sir. Okay, thank you.
Sir, one thing, so this register which has to be written, this
Yeah.
has to be done in that cycle only, like res comma flags equal to ALU ABC something. So
Which
that
register? Which register?
register res.
Yeah. So RES has to be written in a particular state of the controller.
Third state. I mean, it has to be written in third state, only, not in the rising edge of the fourth state, right?
Yeah, yeah. In the third state it will be written. Yes.
So I mean that suppose I'm giving the right enable as 1, then it will be written in the rising edge of the fourth stage. So that we don't want, right?
If you are assigning to these 5 registers inside the clock process, then you don't need to generate the right signals for those.
Okay, got it, sir.
Yeah,
So,
yeah.
so sir, I'm just getting confused. 1 second, like I'm giving 2 states. The next state when I'm going, so that at that time only these operands will get the register. I mean the result will be calculated, and I'm assigning that in the
I
third
think
state.
let me do one thing. Let me write a short note clarifying this. That will help. So
Okay, sir.
in a couple of minutes, I'll do that.
Okay, sir. Thank you.
Okay, thank you. Let me close this.